Hello there, Mr. Sutton here, bringing you the Algebra 2 9-6 lesson on making inferences from experiments. In this one, we're going to analyze data from experiments using something called the experimental mean difference. And we're also going to be resampling data and using resampling to make some inferences about a treatment. And when I say resampling, I mean like simulated 200 times resampling. The techniques we're going to be using on the lists in this lesson can be used on lists of any size. The lists in this lesson aren't super huge, so we could do them without the aid of Desmos, but they are just big enough where Desmos does actually save us some time, and it's a good place to learn how to use these functions. So first thing we're going to learn about Desmos here, just to give you a quick tutorial, is we can create and manipulate lists on there, specifically by creating a list with brackets. So we can define a list using brackets. So for example, if I want to name my list L, I'm going to say L equals, and then I can use brackets with whatever numbers that I need to put in my list. So here's Desmos, and by the way, you need to use the Desmos grapher in order to get a lot of these functions. Some of them work with just the regular scientific calculator, but not all of the ones we'll be using today. So let me do L equals, and then bracket, and we'll do 1, 2, 3, just to put together a very simple list. It tells us 3-element list. All right, awesome. So what can we do once we've got this defined? Well, if you want, anytime you write L now, it'll call back your numbers here. So that's kind of nice, although maybe not super helpful. But what else can we do? Well, we can find the mean of a list. So you can do mean, and then you can just put in whatever variable you used for your list. Or you could put a bracket list in directly here, but it's nice to have this kind of spelled out and be able to refer to it with just a single letter. So if I do mean of L, it finds the mean of my list, which, to nobody's surprise, is 2. What else can we do? We can create dot plots using lists. So the format of a dot plot is you write dot plot and then your list name, comma, b, which is going to be some number. B is going to be your interval length. So typically you want to make it something where you could actually catch all the values in your list. Since I just have 1, 2, and 3, if I make my interval length go by ones, then I should be able to see all these values. But if these were like point, some 1.3, 2.7, things like that, then you'd probably want your interval list to be going by point ones so that you could see those. So let me just show you this. So let me get rid of my mean. Let me do dot plot, and then I'll use my list L, and I'll use the default of 1 for my my interval length. And we see here, if we just expand this a little bit to see the graph, there we go. So we've got a little dot plot, 1, 2, and 3. Now, if my list had more than one of these in it, let's say that I had another 1 in there, I'll just put another 1 in there. Let me try that again. There we go. So now I have a list with 2 of those ones, and we see that the dot plot has changed. Now I've got 2 of those dots. So this can accommodate a list of any size. In addition, we can, if we have 2 lists, actually join them together using the join function. We just do join and then one list name, comma, the other list name. So let me create another list. Let me call it M. And let me say M is going to equal bracket, I don't know, 4, 5, 6. I'm feeling very creative today. And instead of dot plotting all this stuff, let me just do join and then L, comma, M. And now we see that we have a list that has all of that together. So before or after you've joined a list, either way, one other cool thing you can do that we're going to be doing at some point in this lesson is you can reorder the list. And you can reorder it using something called shuffle. So if you just, let me rename my joined list to, I'll call it J for joined. So now I have a J list that has all these elements in it. And now let me go ahead and shuffle that. So shuffle J. And now we see that we have all these elements in a different order. And let me just rename that. I'll call that S. Just again, so I have something to refer to it as. One other neat thing you can do is you can access the elements of a list. let's say that I wanted to shuffle this and take the first 4 elements. So the way this is formatted here is you just do the element number and then a dot, 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 and the last element number of all the stuff that you want. So if I wanted to take my shuffled list, and let's say that I wanted the first 4 items, then I could just write the list name, which was S, put a bracket, and then I want elements 1 through 4, so I do 1 dot 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 4. And let's see, close that, and that gives me the first 4 of those elements. Or I could get elements, 2 through 5 if I wanted. And once you've got these elements, you could, if you wanted to, name it something else. I don't know, let me call this T, and now I've got another list with these elements. So there's a lot you can do to play around with things and not have to do everything by hand. Now that we've got that background with Desmos on things we can do with lists, let's take a look at our problems for the day. All of our examples are going to revolve around these cherry tomato plants. So there's a randomized comparative experiment testing whether a soil supplement affects the total yield of cherry tomato plants. So basically they did a randomized test, which is a good thing, of whether some special fertilizer makes these things grow more. The control group has 10 plants, and our treatment group, which gets the soil supplement, also has 10 plants. And this table is showing us the results. So we have our 10 cherry tomato plant control group subjects and 10 for the treatment group as well. Now there's a lot of ways you can slice and dice this data to see if this supplement is making any difference. One thing we can do, a very simple thing, is find what is called the experimental difference. So basically we're going to figure out the mean of the treatment group, the mean of the control group, and then we're just going to find and subtract the control group's mean from the treatment mean. So basically we're going to figure out how much of a difference on average did this make. And we've seen that we can find means on Desmos, so feel free to pop these lists into Desmos and use that to make things go a little bit faster. Pause the video and let's see what we get. So I don't know about you all, but I'm excited to see what Desmos can do with all this stuff. So I'm going to create a list for my control group. So I'll call it big C equals, and now let me just put all these in here. So we got 1.2, 1.3, 0.9, 1.4, 2.0, 1.2, 0.7, 1.9, 1.4, and 1.7, and close that bracket. Now the nice thing about this is it tells you how many elements are in your list. So although typos are still possible, we at least know that we didn't miss anything, from the list that they gave us here. Now let me go down and make another list for my treatment group. We'll call that T, and I'll do the same kind of thing. So 1.4, 0.9, 1.5, 1.8, 1.6, 1.8, 2.4, 1.9, 1.9, and 1.7. Now it's kind of hard to tell just by looking at these numbers which of these has a bigger average. They look like the same kind of numbers, they're in the same neighborhood, but let's find out if that's actually the case. So let me do the mean of my control group first. So we'll do mean of C, and that's 1.37. And I did this little X bar here because this is just a sample, not the population necessarily, of all tomato plants that could ever exist. And let me also do the mean for my treatment group. So I'll just replace the C with a big T, and that comes out to 1.69. And if we subtract those, we probably don't need a calculator. That's going to be 0.32. So that is our experimental difference here. So it looks like on average the supplement did seem to make some kind of a difference. But what does that mean? For this next part of the problem, they want us to display the data in a double dot plot, and then based on parts A and B, make a conclusion about how much our yield of cherry tomato plants was affected by the treatment, the soil supplement that they used. Now you might be wondering, why do we need this dot plot in the first place? We already found there was an experimental difference between these two groups. Well, the mean can be misleading. If there are a few of these tomato plants that for whatever reason were just off the charts, it could totally be skewing things for reasons that have nothing to do with our supplement. So it helps to see all of the different data points and see if everything has been kind of shifted one way or another. And that's where this dot plot can help us out. Now you might have noticed on Desmos when we did our little intro that you can do dot plots on Desmos, and there is kind of this inclination to maybe plot both of these at the same time and see what it looks like. Unfortunately, that tends to make things a little bit more confusing because the dots from one group can cover up the dots from the other group, and then you can't really tell, where things are in relation to each other. So I recommend, if you're going to do Desmos, that you use a separate number line for each of these dot plots. So plot one of them, graph it out here on paper or wherever you're graphing this, and then do the other one. Feel free to use Desmos to help you, and then put the other one out. And try to line the number lines up so that, for example, 1.7 on one number line is in roughly the same place as 1.7 on the other, just so you can get a picture of how these things have been shifted. So pause the video and try that out, with or without Desmos. Alright, again, I'm going to use Desmos to give myself a little bit of a guide here. So back on Desmos, I am now going to do dot plot, and I'll do the control group first. So I'm going to do dot plot, parentheses, C, comma. Now my interval lengths, since we see this data for both of these is rounded out to the nearest tenth, I would think 0.1 is a much better interval length than 1. If we do 1, then things are just going to get shifted one way or another, and it's going to be confusing. If we do 0.1, then we can actually look at this a little bit more finely. So there we go. We've got our dot plot for the control group, and I'll expand this a little bit so that we can kind of see what's going on. And let's see here. We've got, this is 0.7 right here, 0.9, and all the rest of these. So you could make a number line on paper and then just kind of transfer these on there, like so. And you'll see here at 1.2, if we look right here, we have to go up a little bit to see it, maybe zoom out a little bit. But yeah, there was another dot at 1.2. So you have to play around with this a little bit, but you'll at least see all the dots that should be on your dot plot. Now let's do this again for the treatment group. Here's the treatment group with a dot plot, and we see that things have, if you just keep switching back and forth, you can kind of tell things have been shifted a little bit to the right. So here is all the things you would see if you zoomed in on Desmos for your treatment group. Now, just taking a look at these things, based on the mean difference, which was an experimental mean gain, and also based on this, where it looks like everything got shifted a little bit to the right, this allows us to conclude that the treatment appears to slightly increase the yield of tomato plants. I mean, there wasn't a drastic increase necessarily, but, there's definitely something going on there. For this next problem, they're asking us to resample the data in example 1 and then use the mean yields of the new control and treatment groups to calculate the difference of the means. So what's all this about? Well, resampling means randomly reassigning members to a new control and treatment group. The idea here is, we're trying to leave open the possibility that maybe we just got lucky the first time around, and it was just kind of happenstance how things played out. Maybe if we reassign everybody and recalculate the means, if we end up with a new experimental mean that is similar to the old one, that would show that the treatment actually wasn't that effective after all. We got a certain mean growth the first time around, but if we get the same sort of growth with the mean with every other possible random rearrangement of this, then maybe it isn't all about the soil supplement and it's just something weird about the numbers. So there's a lot of ways you can do this. You can do it by hand. Typically, though, we use technology for this reassigning business. So on Desmos, a quick way to do this would be to join and shuffle the original control and treatment lists, and then you can find the mean of the first half and the second half of the new kind of joined shuffled list that you've created. So pause the video and use Desmos or don't, but see if you can come up with a new experimental difference. All right, again, I'm going to go with Desmos. So here's Desmos, and here's my two groups that I created for the control and the treatment. Let me go ahead and I'm going to combine a few steps here. So I'm going to create a joined and shuffled list that I'm just going to call S. And that is going to be what happens when I shuffle, and then parentheses join, and then parentheses C comma T. I could break this up into more steps, but I don't really need to. So we see here that I joined my initial two lists and then shuffled it right away, and that gave me a new list of 20 elements. So I just want to find the mean of the first half of this list and the second half of this list. So I'm going to do mean of, and then I'll do S, and then 1 dot 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 10. That gives me the first half of my S list here, and that comes up with a mean of about 1.73. And then let me do a mean of S, and then 11 to 20. That gives me the second half of my list, and that's a mean of 1.33. So that's a difference of 0.4 or negative 0.4, depending on which way you subtract these. So this is what I did when I ran this this time around. When I originally made this slide, I got different things because, well, that's the whole thing. When you shuffle it, it randomly reassigns things. So you might get totally different numbers than me, and that's okay. So the first time I did this to get my initial PowerPoint numbers, this was my new control group, all these numbers. Feel free to write these down or keep whatever ones you came up with. And here was my new treatment group the first time I tried this. And then my mean difference of these groups, I had 1.6 for the control. I had about 1.46 for the treatment, and that came out to roughly negative 0.14 when I subtracted those. But again, there's a wide variety of different differences that you could come up with depending on how you randomize these things. So that resampling was kind of interesting. We got a negative 0.14, which is a lot different than the 0.32 we got initially. So that seems to suggest that 0.32 actually was significant because we didn't repeat it by just reshuffling the data and rerunning the numbers. But one resampling isn't really enough to base your theory on. So we're going to take it a step further here. To conclude that the treatment in example 1 is responsible for the difference in yield, analyze this hypothesis. The soil nutrient has no effect on the yield of the cherry tomato plants. Specifically, here's how we're going to analyze this hypothesis. Compare the experimental difference of 0.32 from example 1. That's what we got when we did that example together. Compare that with the 200 simulated resampling differences shown below. So essentially, we did that little resampling process and figuring out new experimental differences. They did it 200 times for you and put all those numbers in here, the frequencies of all those new experimental differences down here. So based off of this, what can we conclude? Does the soil nutrient have an effect on the yield? Now, to kind of guide your process while you're comparing this with these this frequency table here, this histogram, if this hypothesis is actually true, if the soil nutrient has no effect on the yield of cherry tomato plants, then we would expect that the mean difference ought to be 0. So with that in mind, based on what your mean difference ought to be if this hypothesis is true, see if you can reject or accept that hypothesis, and using this table, pause the video and then see what you can conclude about that effect of the soil nutrient on the yield. All right, so here is 0 roughly, and we see there's a very high frequency from resampling. But this 0.32 is actually way over here. This is to the right of most of the results that we got with this random resampling. It's very unlikely that we would get that just by random chance. There has to be something to it if we're this far to the right of kind of the expected value if this hypothesis were actually true. Based off of how far off that is from the center of our data, we can reject this hypothesis. Since the hypothesis was that the soil nutrient didn't have any effect, rejecting that means that we're accepting the claim that the soil nutrient has a positive effect on cherry tomato plant yield. So this concludes our time analyzing and making inferences from experiments, and also is the end of our journey with the noble cherry tomato. I'm going to go make a salad now. Until next time, Mr. Sutton signing off.